Hello, and welcome to this live webinar from IVT in association with Parker. My name's Tom Stone. I'm editor of IVT International magazine and its various platforms, including this webinar platform. And I'm joined today by two experts from Parker. We have Andrew Kelter and Richard Nagel. I will introduce you a little bit more in a moment, but just to say this is the webinar. You are in the right place for practical considerations for applying ePumps in mobile equipment. And as we know, the off-highway equipment industry is moving towards hybrid and electric vehicles. And so electro-hydraulic pumps, or ePumps, are central to this transition, serving a vital role across applications. So we're going to find out a little bit more about ePumps and the evolution of ePump connections, maintenance challenges, orientation guidelines, and much more. So before we get started, I should just draw your attention to Q&A. There's a Q&A tab to the right of your screen, and if you want to type a question at any point, you can put it in there. We will see it, and after the presentation, which is going to be about 40 minutes, I think, we will get to the questions at the end. So it's a live Q&A. We'll get through as many as we can, but any that we can't get to, our experts will be able to contact you afterwards. Now, anything else? I should also say this is recorded and will be available on demand. So if you want to share this with your colleagues, this will be available on demand afterwards. I think that's probably all the talking I really need to do for now, apart from just to introduce Andy and Rich a little bit more. Andy is business development manager for Parker with over 25 years of experience in the fluid power industry, working for a variety of companies with both components and complete system solutions. Andy is responsible for Parker's HPS business development and product management of emerging electrification technologies, such as ePumps and ePTOs. Rich has over 30 years of experience in the motion control industry, having served in various roles, including field sales, field applications, product management, operations, and global business development. Rich was a marketing director in the commercial vehicle industry prior to returning to Parker in April 2022 to join Parker's new Electrification growth team. So it is electrification, the word on everyone's lips. So without further ado, I will hand over to Rich and Andy for their presentation, and then I'll be back at the end to chair the Q&A session.
All right, great. Thank you, Tom. And thank you, and good morning and good afternoon for all of our attendees. We appreciate you taking the time. So, both Andy and I, we spend a lot of time training both customers and our channel partners. And what we historically find here with electrification, especially on the hydraulic side, there's the folks that are very, have a lot of expert knowledge about motors and drives, and then we have hydraulic engineers. And so we spend a lot of time discussing the intersection of those two technologies. And that's part of what today's discussion is, a little bit more practical based on lessons learned that we've done globally testing ePumps, but obviously motors and inverters play a big role in successful application of ePumps. So when we talk about ePumps, let me make the screen bigger. So, there's really three parts, at least three parts, typically more, but, we start off with a pump, of course. And in this case, since we're not driving off a PTO or an induction motor, we need some kind of a prime mover, right? And in this case, we'll talk a little bit about the differences in motors, but we and most of our industry has moved towards permanent magnet AC motors, and we'll go through a little bit of the advantages. There's obviously some disadvantages too, but obviously very efficient, very wide range of speed operation, very good control from PMAC motors. And then, from the pump side, there are a variety of pump technologies out there. And we'll talk a little bit about the different technologies, what's better suited for electrification, what creates some challenges. So pumps that might have worked fine off a PTO, it may present some challenges with electrification. And of course, these PMAC motors and most of these motor technologies require a drive control. So, we have to convert the command, whether that's a speed command or a torque command, to, in this case, a three-phase control, taking power off the DC battery. So the inverter essentially is a power converter. There are a variety of different sizes from low kilowatt up to 250 up to 500, right? You've got some traction applications that require a lot of current, a lot of power. And then lastly, one of the things we want to talk about today is the coupling of the pump and the motor. And it's actually a really critical consideration, because with a lot of electrified machines, the pumps and motors are buried deep in the chassis. They can be very hard to access. So while these are mechanical devices and they require periodic maintenance, limiting that maintenance or trying to minimize it altogether is really critical for fleet operation, because you don't have to go inside the machine every 6 months to grease the connection between the spline of the pump and the spline of the motor. And Andy's going to talk about some different options and lessons learned through our testing over the last couple of years. So there's a wide range of motors available that we find in electrification. Switch reluctance, DC brushed, very simple control schemes, axial flux, induction motors have been around forever. Our industry has kind of settled on PMAC, at least for ePumps. When you look at traction applications, that's a little bit different, but for ePumps, PMACs offer really a kind of a nice combination of high torque density, high power density, which is really critical. Smaller the envelope and the higher the torque, usually the more successful we are in the application. PMAC motors do have a certain amount of control complexity. You do have to have a drive that converts the DC power to three-phase AC. There's some algorithms involved with that. There's typically bus communications and some safety in the drive. The efficiency of PMAC motors is very good, typically, depending where you operate on the motor curve, 95%, 94%. And PMAC motors have a really wide range of operating speed, down to very low RPMs, up to 7,000, maybe 10,000 RPMs. So you can do a lot of things with the PMAC motor. Of course, one of the trade-offs is they tend to be more costly than induction motors or DC brushed, but they are probably the most prevalent type of motor we use. And there are some things in the topography of the motor that are considerations too, that we'll talk a little bit about on the following slide. So when we talk about these mobile motors, there are different frame sizes, and we typically catalog our motors by the external ID. And of course, from a design standpoint, one of the critical considerations besides torque and speed capability is envelope. And we're often looking at very tight envelopes for electrified machines. So we typically have two choices. We can achieve torque and speed with a lot of different combinations, both diameter, length of stacks or number of winding stacks, also the type of winding. So there's a lot of different variables in motor selection. From a Parker motor standpoint, our GVM, which we've had out for about 14 years, we have three frame sizes: 142 millimeter, 210, 310. Most of our ePump applications are satisfied by a 142 or a 210. There are some big applications that require a 310 millimeter, but that's a lot of motor. Now, each one of these frame sizes has up to 6 lengths per each diameter, and then a number of motor windings. So a lot of considerations when you select a motor, and there's thermal characteristics along with that, upper speed operation, low speed operation. So lots of things for the design engineer to look into. And then obviously on the electrical side, these motors can be wound for either low voltage, 24, 48, 96, or high voltage, which typically is 650 nominal and normally about 800 volts DC today for most of our ePump applications. You can get your lots of frame lengths, lots of stack lengths, different windings can achieve the same speed and torque specs. So you have to understand a little bit about what your criteria is for getting a successful application of a motor. The other thing with motors, there's lots of different cable terminations out there. You can do something as simple as a gland and a spade lug, or a power lock connector, which is like a positive contact connector. The other thing with these types of motors, they are on a chassis, they are outdoors, they get a lot of vibration, a lot of environmental concerns, so water ingression, cleaning solvents, even road salt treatments. So these motors go through a lot of testing and validation to meet the J1455 vehicle standards and the ISO 16750 for shock vibration environmental. So you can't just take an electric motor off the shelf. You need something really designed for a mobile type application. So we won't get into too much of the construction of PMAC motors. You could spend a lot of time on that, but it is important to note that, you know, PMAC motors, they utilize rare earth magnets along with ferrite magnets, typically on the rare earths neodymium or samarium cobalt. They both offer similar levels of performance. You know, we do not require a separate excitation of the rotor magnetic field. We do get a very high density of the magnetic field strength. And then, you know, it's from a motor performance and for ePumps versus traction, which typically are the two sides of this equation. Certain motors might be better suited for one application or the other. The rotor construction has a lot of influence on the performance of that motor. There are essentially two types of rotor construction. We can have the magnets mounted on the exterior of the rotor, and then they have to be typically bonded or sheathed somehow. Or we can have magnets inserted into the interior of the motor. And then we get into, you know, things like saliency, which come with an interior permanent magnet design. And we won't get into really the concept of saliency, but a salient motor can provide very high performance or high efficiency at lower RPMs. And so when we look at ePump selections, obviously we're not running at 7,000 RPM. We're typically running at 2,500 or 2,000 or 3,000. So there are different things in the motor considerations that the application engineers have to look at. Andy, I'll pass it over to you.
Yeah, thanks, Rich. Yeah, so when selecting an ePump, obviously it's important to pick the best type of pump for your application. And you know, what we like to say is that the pump that you used with an internal combustion engine or off a PTO shaft might not be ideal for use in electrification application. So here's 5 different pump technologies. I'm going to talk a little bit about what are the strengths of each, just to give you some thought into your application. Gear pumps in the top left are kind of tried and true, used in a number of mobile applications quite successfully. They tend to be, you know, low cost when you think about the initial purchase price of the components. But again, maybe some trade-offs there on efficiency and noise that might not make it the best fit for electrification. That's up to you to decide. Helicoidal gear pumps are kind of a newer technology, especially for mobile applications. They tend to be very, very low noise, so low sound levels or low decibels. And that makes it attractive for electrification. Obviously, when you remove the combustion engine, other components now you know, come to the forefront. And so the noise of the pump might be a consideration and might lead you to a helicoidal. Again, some trade-offs there in durability and efficiency that you need to weigh when making the selection. Bent axis piston pumps in the top right. Typically, we think of a bent axis being used more as a motor, but they can also be used as pumps, and they work quite well for this because they have very, very high efficiency levels, and efficiency translates into, you know, lower battery consumption or longer runtime with a given battery, which can really reduce, you know, either the price of your machine if you're able to reduce the batteries that you need to put into it, or extend the runtime on your machine, which is also an attractive feature. Axial piston pumps also really good efficiency, so lower battery usage. And the advantage of an axial piston pump is because they're variable displacements, you're able to you can potentially minimize the motor size with the ability to control the torque input. So by reducing the displacement of the pump, you reduce the torque required from the electric motor, and you can sometimes downsize your electric motor depending on your duty cycle, which can again save in weight and space claim and of course cost. And then vane pumps in the middle, I like to think as a nice compromise between the technologies. They're relatively inexpensive. They're pretty quiet, so low sound level, and they have decent efficiency. So if you're trying to weigh all these factors together, sometimes a vane pump can be a nice compromise. As Rich mentioned in his intro, there are different ways to connect a pump to an electric motor. We've been connecting pumps to electric motors for many, many years, obviously, right? And when you think about industrial power units, and typically that was done through a bell housing and coupling arrangement, like you see on the left. But for mobile equipment, we don't believe that that's the best approach. You want to save space and weight and reduce components. A direct male to female spline connection or the close coupled option is a better choice here. And also it's going to give you tighter operational control. I'll go into it a little bit. The warning with the spline connection is that lubrication is required. You do have metal to metal contact, and that lubrication is crucial to the performance of the ePump. So when I mentioned operational control, if you think about the coupling at the top with the flexible insert, the red portion, sometimes it's called a spider, works well in a fixed speed application, such as a traditional PTO shaft, or in an industrial application where you're connected to the grid and spinning an induction motor at 1800 RPM, 1500 RPM. That coupling arrangement works really well. But in electrification, electrified mobile equipment, you're going to want to accelerate and decelerate that electric motor to really match the flow output from your ePump to your system's requirements, right? And you're going to want to accelerate and decelerate in milliseconds, right? And so having the direct spline connection is going to give you that tighter dynamic response and the tighter operational control that's very important in these applications. With the spline shaft, there are some things that you need to consider and need to bring into your selection criteria. One of them is the spline tolerances and fit. You want to make sure that the pump and motor are matched dimensionally and tolerance-wise, and that proper alignment is occurring during assembly of the components, so you don't get binding and drag or premature wear. Also, the shaft metallurgy and heat treatment are important to make sure, again, that they're matched to each other, that you don't want the shaft to be under or over heat treated where it could fail prematurely or cause the mating component to fail. And the last bullet is really the important one. It's fretting corrosion. It's the need for proper lubrication to prevent fretting corrosion in that spline arrangement. And what is fretting corrosion? Well, it's it's in essence a failure mode that's experienced in areas of high contact stress and where vibration is occurring. So this certainly holds true in off-road or even on-road mobile equipment. You have the vibrations are there. And you have high contact stress. The picture here is a shaft from our test lab, and it's typical of the evidence you see from the beginning of fretting corrosion. You'll see this rusting and wearing on the splines, and this shaft is, while still functional, you'll start to lose some of that dynamic control, the operational control, as the components wear. And eventually the shaft will wear to the point where it's no longer functional. And as Rich alluded to earlier, some of the challenges with maintenance and why you want to make sure that the components, that the splines are going to last a long time, is that oftentimes the ePump is buried deep inside the machine as a function of where it ends up due to the layout of the machine and the need to fit so much in a small package. And so, we've had stories from certain OEMs where it's taken many hours to remove the ePump from the machine, do the maintenance that's required on it, and then reassemble it back into the machine. And that's really downtime that you and your customers don't want or need, and can be avoided by the proper spline lubrication. And so what we're proposing to the market is really a three-phased approach to spline lubrication. It's a good, better, and best solutions. The good is grease. Grease is a very good lubricator, and the right grease, proper grease, is going to help to give long life. However, not all greases are created equally, and you need to make sure that you're using a grease that's appropriate for the speed and the temperature range that it's going to be subjected to. And also, even the best grease is going to need to be replaced over time. I mean, we all know that, right? Any greased location has to be re-greased at some interval, whether that's 6 months, 2 years, or 3 years. Depends on your duty cycle and your application, but it's going to need some maintenance to it. So what we have as a better approach is a wet spline, and this is using hydraulic oil to lubricate the splines, which we've done with like our Chelsea PTOs for many years in a wet spline arrangement. And it's convenient in an ePump. Obviously, we have hydraulic oil available, right? The pump is right there. So all we need to do is remove the shaft seal from the hydraulic pump. We put a special shaft seal inside of the PMAC motor to seal off that cavity, and the case oil from the pump lubricates the splines. This works really well. However, the limitation here is that we only advise using a wet spline in a horizontal mounting orientation. The reason for that is if you mount the ePump vertically with the motor above the pump, you're going to create a pocket of air at the top of the oil, and that air is going to be right where the splines are. So you're not going to get the lubrication that you need out of it. So what we've come up with to mitigate that and to allow for a wet spline orientation in a vertical orientation, is our maintenance-free spline connection. And this is, again, we expose the splines to the case oil from the pump, but we're also able to actively flush oil across the splines to remove that pocket of air in a vertical mounting. And so how does this work? Essentially, like I said, we remove the shaft seal from the pump, we put a special shaft seal in the PMAC motor, and then we have some special machining in the shaft of the pump. So as the shaft rotates or spins, it creates a centrifugal force that then pulls the oil and any pocket of air down through the center of the shaft and replaces it with fresh case oil around the outside of the spline. So you're constantly flushing the spline connection as the shaft spins. The nice thing about this design is no additional case drain is needed. Everything happens internal to the ePump. So to you and to your customers, it's all invisible. It all just self-lubricates as the shaft is spinning. Our testing has shown about an 85% reduction in spline wear by using this maintenance-free solution versus grease spline. So, really, really good results. And again, it's a fairly straightforward approach to lubricate the splines. And why might that be important? Why might you need a vertical mount? Well, I mean, the first thing is to help in your machine design. Oftentimes, it's easier to mount the ePump vertically from a space claim standpoint than it is horizontally. So if you can mount the ePump horizontally, of course, that's fine. But if you need that space or that freedom of mounting it vertically, it's a nice feature here. Another reason is for assembling the ePump into the machine, lifting an ePump vertically, you don't have to worry about the center of gravity like you do on a horizontal ePump. You can just lift it vertically, drop it into your machine, and off you go. And then the last reason is really for a vertical orientation. You can oftentimes mount the pump lower relative to the reservoir, which is going to give you better suction characteristics on the pump. So the lowest you can mount the pump relative to the reservoir, you're going to get better suction into the pump, which allows you to really run the pump at its rated speed and take advantage of the higher speeds that PMAC motors can give you. So to summarize here, greased or maintenance-free splines can be mounted horizontally or vertically, but the wet spline design, we only recommend mounting horizontally. And with that, I'm going to turn it back to Rich.
All right, thank you, Andy. I was just reconfiguring my screen again. Okay, so some other considerations from practical aspects of ePumps, and you know, a lot of these you'll see here and through illustration. You know, they're inversely proportional, and so of course some of the things that hydraulic engineers didn't have to worry about with traditional ICE propulsion now become a bigger deal, right? And efficiency is really important, obviously, for electrified systems because the power available, right, is not, it's finite. And of course, there's charging involved of the battery. So, you know, what's critical is utilization of the machine. And so efficiency, of course, is one of the enemies of good efficiency. What I would say, you know, hydraulic systems generally are, there is some inefficiency in hydraulic systems. It's not just the pump. It's if you have valve control, fluid conveyance fittings, you name it, you can have small power losses. They start to add up. So it's critical that we try to maximize efficiency when we can to try to get as much battery life that we can from that device. So, you know, one thing that we find, right, from an efficiency standpoint, and we'll show a nice illustration of this, kind of the dividing line, right, is high duty cycles, high pressure, lower duty cycles, lower pressure, right? And, you know, that'll very often drive the decision for what kind of pump you want to use. And, you know, we always tell people too, there's a lot of industry considerations for pumps. Certain industries just have migrated towards certain types of pumps over 50 years. What you'll find, right, in electrified systems is that maybe that's not the most efficient selection, might be cost effective from an acquisition standpoint, but maybe not from a total cost of ownership. So, you know, we tell people, you know, pick a really good pump selection because over 5, 10, 20 years of operation of that machine, those efficiency costs, right, or costs due to poor efficiency really add up. So, you know, it may require you get a better pump, and we'll define what better means, to offset, you know, this utilization to try to maximize it. And of course, the other side of this is noise, and noise, of course, is very subjective. And you know, in the world of diesel engines, noise really wasn't the biggest consideration. But I mean, we see this time and time again. You go to a electric drivetrain, and now all the auxiliary equipment becomes the most annoying thing on the machine. And whether it's a hydraulic pump or an air compressor or a water pump, all of a sudden these things become much more important for the machine builder. So once again, there's these inverse relationships. Pumps with lower noise are typically less efficient and better suited for low duty cycles, things like steering or maybe a lift that is only operating a few times a day. And of course, you know, you get piston pumps, which, you know, very efficient, but also noisier. And we talk a lot about sound quality because, you know, we talk about decibels, but also you have to look at frequency and the combination of the two and how the sound waves are emanating. So things like shrouding can, you know, affect noise. The operating speed of the pump has a huge effect for the hydraulic pump. Any kind of dampening we can use, let's say motor mounts, pump inlet conditions. And then once again, we tell people, you know, you can reduce the pump speed, but then you might be operating at a point where the motor's less efficient, and you may have to then upsize to a bigger pump, which costs more money. So there's all these trade-offs with ePumps and electrification that generally aren't true for diesel engine applications. So I like this graph. This is this inverse relationship between noise and efficiency. And I think what stands out on the top line, which is your decibel line, you know, your diesel engines are operating in the 100 dB range. And when they're running, you don't really care about much else. But you take that diesel engine out, and all of a sudden, let's say we have a bent axis pump, very high performance pump, but may operate in the high 80s, low 90 dB range, depending on the speeds. If you go to the other end of this continuum, you have the helicoidal pumps, very quiet, 60 dB, and throughout a lot of speed ranges. And then we kind of work up on the noise continuum to vane pumps, gear pumps, and there's a little bit of a gray area between those two, depending on the construction of those pumps. But then your piston pumps and your bent axis generally are the noisier of the two. But then again, there's frequency considerations. So you have to measure out the amplitude versus the frequency of the noise to make a good decision. On the other axis, right, in his counter is efficiency. So of course, the most quiet pumps tend to be less efficient. The noisiest pumps tend to be the most efficient. And you could also overlay cost. Not always, but you can pretty much assume that you pay for efficiency. You may also pay for lower noise, right? Because a low-cost pump that's noisy and inefficient may not work for electrification. So you may be looking at something like a vane pump. And Andy had mentioned earlier that that's a great kind of in-the-middle pump to consider. But once again, we have lots of pump options. There's not one that's perfect for all electrified applications. And there are control options available with the axial piston pump, the variable volume pump, that you can't get with the other products that can be very interesting too. So sizing, once again, it's a little daunting. I think hydraulic pump engineers, if you grew up with hydraulics, pumps inside out, and all the characteristics at the different speed ratings, pressure ratings. Same is true for motor engineers, right? Application side. But a lot of those all those sizing considerations have to be accounted for the ePump, because now we have the pump and the motor. So we always start off with battery voltage. So if we have a sizer tool, or you're talking to an app engineer, one of the first questions is, what's the bus voltage? Is it 650? Is it 300? Is it 96? So we typically start there. Are there any current limits that we need to consider? That's tied to voltage always. And then, understand the application type. And what's really critical for electrified equipment that I think hydraulic engineers don't consider is duty cycle. Understanding what is continuous versus peak. What is your RMS duty cycle during the day? What's the duration of the operation? Are you running 8 hours? Are you running 2 hours? There are a lot of pressure spikes. Pressure spikes typically get introduced by the work at the actuation point. Not all applications have a lot of pressure spikes, but there are some that do. That drives your pump consideration. Noise tolerance. Is this equipment in a city where there's pedestrians and other people who are really annoyed by high noise? Or is it in a remote construction site where that noise really isn't important? And so then, of course, we have to operate at speeds. And we've talked about this both from the pump and the motor standpoint, that optimize efficiency and reduce noise. So once again, we have motors that can run at very high RPMs and pumps that can't. Online sizing tools can help you select ePumps in eMotors using different variables. I'll walk you through a quick screenshot of what we use here after this slide. But what's important is we always talk about this intersection between hydraulics and motor sizing. And one thing we find all the time when we do training is especially in North America, our hydraulic engineers speak in terms of flow and pressure and horsepower. So a lot of imperial units. If you talk to a motor application engineer, they only talk in terms of duty cycle, motor speed, and torque. And so they typically go right to this torque curve, and they look at, let's say, the blue line, which is continuous, or the red line that's peak, and then they figure out what's the best case motor that can be applied. But we find sometimes they're like two different languages. And so software can help interpret between those two languages, but we tell people it's always very important to understand your duty cycle, because there's a lot of cost if you size continuous, but you can actually operate in peak. Because if you can operate in peak, you can downsize the motor. The pump doesn't really care so much. The pump's kind of designed to run in continuous mode, but motors have a different design criteria. It's also based on thermal conditions, how much cooling flow. So those are all important considerations for sizing. So we do have software tools. For example, this one is web-based. It is somewhat limited, right, because it is an open product, but we categorize applications rather than, hoping that people know what types of pumps are best suited, right? We break this down into like 3 general applications: lower noise, pretty easy to understand; heavy duty, also pretty easy to understand; and then balanced. Balanced is typically moderate duty cycles, 20 to 40%, pressures below, let's say 200 bar generally, or 3,200, 3,300 psi. And so a pump motor sizer, and there are different products. There is a pump, ePump sizer, and a motor sizer, but an ePump sizer will take your application, take your flow and pressure data, convert it to torque and speed. It'll then give you some best fit pump selections, and it could be based on ranking. Maybe a vane pump is the first choice and a gear pump is second, and on and on. And then once you select the pump and it picks the right pump displacement that can operate where it needs to operate, it'll select the best fit motor. So take the best fit frame and length and winding for that application. It'll plot out then torque speed. So it gives you some information, gives you kind of the basis of an ePump part number. And it's not a foolproof tool, but it gets you very close and allows you to speak to an application engineer to get more information. But there are other considerations on the motor side that aren't always considered here, that take somebody sometimes a little more experience on doing applications to help you. But this is a great start, especially for helping pick the motors and get you in the right area of the pumps too. So Andy, I'm going to pass it back to you now.
Yeah, thanks again, Rich. Yeah, with any manufacturer, it's important to make sure that the ePump has been properly lab tested first. I mean, obviously you want to test it on your machine, but to have that assurance that it's been lab tested, in the right orientation, across the speed and acceleration range that you need, with the right pressures and flows. So having that lab testing and the assurance that the ePump's already been tested is going to save you development time and money when implementing into your machine. And at Parker, we've invested pretty heavily into our testing capabilities across the globe at a number of different sites. But I wanted to share some images from the facility I'm based in, which is in Marysville, Ohio, just outside of Columbus. And really the investment we've made into world-class testing capabilities. We can do performance, so across the operating range, sound levels. We can do performance and sound simultaneously to really map out where the best criteria, the best situation for your application is, and also endurance testing. So all these different spline lubrication options, we've put them through millions and millions of test cycles to really validate the components, as well as just the interaction of the pump and the motor to make sure that are there axial radial loading from one component? How's that going to affect the bearings in the other component? And to make sure the pump and motor are a match set. We also have a lot of capabilities to mimic customer applications across a number of factors and duty cycles, and it's kind of as a service to help our customers in your electrification journey. And Rich explained, the sizing tool that we have available on our website. Obviously, behind the scenes, we have a lot more advanced analytical tools that we can use, along with our application engineers to really help to optimize your system architecture. And another point I want to make is just not to underestimate the value of using a complete ePump from one source. I mean, obviously you're going to save on the labor of assembling the components and the number of purchase orders that you need to issue, but really you're going to make sure that you get the latest in lubrication technologies. We're continuously testing new greases. Obviously, our maintenance-free spline is only available if you buy the complete ePump because of the internal changes that we need to make to the products. And you're going to get the peace of mind of having a matched pump and motor, and even extending that to the inverter and the controls. I think we like to pride ourselves that everything is designed to work together seamlessly. And to pull all this together, Parker has established a couple of mobile electrification centers. So we have our center in North America is again in Marysville, Ohio, and in Europe it's in Offenburg, Germany. And these centers, our charters are really operationally to execute on this putting these components together and building complete ePump systems, but also our engineering and test lab capabilities, as I outlined before, to make sure that we can help you specify the right equipment and get it tested properly before implementation into your machines.
Yeah, and I'll take over. So yeah, once again, I'd like to thank IVT Expo and Tom for hosting us today, and thank you for everybody who attended. I haven't seen the final count, but I'm sure we'll get that. I guess just a note, this is tied into the IVT Expo, which is an off-highway vehicle summit. It will be occurring August 21st and 22nd this year in the Chicago area. It'll be a very exciting week in Chicago, just for anybody who's traveling that week. But it's at the Donald E. Stevens Convention Center, formerly known as Rosemont, near O'Hare Airport. Both Andy and I will be there, along with a number of other Parker folks on different technologies, not just motors and pumps, but also on fluid conveyance and sealing. We'll be at booth number 1226, so please stop by, chat with us about ePumps or anything electrified. We'll be happy to help you and talk. And so with that, I'd like to once again thanks Tom and IVT for hosting us today, and Andy, thank you for all the work done here.
Brilliant. That's great. Well, we'll certainly look forward to seeing you in Chicago. But before we get there, we'll jump into the Q&A, because we've got a few questions coming in here. So we've got a bit. We'll try to finish at the top of the hour, but we've got time for some questions. So get your questions in now. I'll get to them now. I just wanted to ask a question though before we get going about the what types of grease would be appropriate for ePumps, and does that affect the service life, the type of grease that you might use?
Yeah, I can take that one. So there's a lot of different greases out there, and a lot of different choices that can do the job. We tend to recommend our Parker Chelsea PTO grease that we've used in PTO spline shafts for many years, and it works really well. But we're continuing to test other compounds, some newer grease technologies, and we might have a recommendation in the future to change to something else. But for now, that's kind of the recommendation we make. Great.
Some really interesting information throughout the presentation there, and I think a couple of people asking if they can get slides. I think if they contact you, they should be able to get slides if they contact you afterwards. But to jump on with the questions now, leading on from my question there, what about cooling? What motor cooling options are currently used, and is immersion cooling being considered? If so, is that a separate fluid or the case fluid?
And do you want to take that, and then I can jump in too?
Sure. Yeah. I mean, on our GVM series of PMAC motors, we actually have a patented cooling design that really puts the cooling tube flow right down into the stator, which gives you the maximum heat transfer, and it improves the efficiency of those motors greatly. Typically a water glycol is the recommended cooling fluid. You can use hydraulic oil. It's not quite as effective at heat transfer, but you certainly can use it. And typically we do, need some type of a cooling fluid to cool these motors.
Yeah, and also I would throw in, along with the with the motor, right? You have the power electronics in the inverter. Mm-hmm. Inverter, if you're passing 250 kilowatts of power, right? A lot of power in through the inverter. So, we typically spec something like 12 to 15 liters per minute of cooling flow. At 60 C is kind of the recommended nominal. If you can get a colder fluid, right, you can do more things, right, with peaking and just power efficiency. But water ethylene glycol is probably the main fluid that we use, and typically the battery systems need it too. So we're just usually running right off a centralized cooling system.
Excellent. Thank you for that question. Here's another one. Looking at the pictures, it looks like a pump in tank solution is most suitable for the maintenance-free spline. Are you able to submerge a variable pump in an oil bath, especially taking into account the electrical connections in the pump?
Yeah, so the short answer is yes, you can submerge a variable pump into a reservoir. We do it in industrial power units all the time. Typically, you'll want some type of a hydraulic control then, or maybe you move the electric control up to a safe area outside of the reservoir. But yeah, it can be done. The electric motors, it's a little bit trickier, but there are some constructions where it can be submerged to get that direct cooling. Yeah, there's all kinds of ways to solve these problems, right? Yeah.
Great, cool. We'll move on to the next question. Let's see. A lot of your slides and visuals show bent axis pump as a choice for ePump. Do you see this as more popular because of any reason like cost, for example?
So I'll start off and then Andy can finish up. So Andy does a lot of work with the bent axis. So bent axis is not the most cost-effective solution, right? The bent axis pump is the shining star of the pump family in terms of speed ranges, low speed, high range, pressure spikes, life, right? So it is intended for very heavy duty applications. And of course, efficiency is critical throughout the speed range. And that's one nice thing with the bent axis. It will achieve 94, 95% efficiency, even at lower speeds and high pressures where most pumps start to really fall off in efficiency. But Andy, once you've done a lot of work with bent axis on electrification.
No, yeah, I think you nailed it there, Rich. I mean, efficiency is often the key, as you said earlier, to minimize the number of batteries that you need in a machine to get your runtime to get a day's work done. So the bent axis really does shine there because you can optimize that efficiency and minimize your batteries that you need.
So you got lots of pictures of the bent axis one because that's your favorite.
I don't know about my favorite. I tend to be a piston pump person, but yeah, the axial piston pump has benefits too, with the ability to control the torque from the motor.
Depends on what you want to use it for.
Yeah, exactly.
Yeah. How often? Well, there's another question about grease. How often will it need to be greased? Is auto greasing recommended?
I don't think we have a mechanism to auto grease because it's difficult to get grease inside the electric motor where the female spline is located. And how often it needs to be greased, our engineering team has put together some nice tools. What's important really is the speed of the shaft, the RPM, how fast it's spinning, and the temperature at the grease. And it's very difficult, obviously, you can't measure the temperature at the grease. So we back it up and we measure the winding temperature of the electric motor, and we're able to estimate what the grease temperature is likely to be. And we have some charts and tables that we can provide to customers for specific applications. Obviously, we don't want to give away all the secret sauce in a web forum like this, but we do have some estimations we've made on how often you might need to regrease, depending on how hard the winding temperature and the speed of the motor.
Yeah, I would also throw in, I think one of the things that people don't always understand, one of the really positive aspects to electrified systems, that drive inverter collects a lot of data and can generate a lot of data. So at any time, we know the motor speed, we know temperature of the windings, we know torque, right? Because we have current consumption. So, a machine controller can start to calculate RMS work cycles, baseline efficiency versus field efficiency, and you can really look at a work profile over time. And so with the telematics solution, right, if you broadcast that data and you have a pretty good understanding of your work duty cycle, that can start to give you some indications of when it's time to change grease, right? We don't necessarily have to live in the world of like an oil change, right? Every X thousand miles, right? You take the car in. We actually have the information, right? If the customers are savvy enough to know what to do with that and broadcast it through telematics, you can start to get some pretty good estimates about how much work you've actually done, how efficient your systems are. I mean, it's really the beauty of the electrified system. It's just it's a data machine.
Excellent, thank you. What application parameters benefit the use of eDrive solutions with fixed speed variable pumps over variable speed fixed displacement pumps?
Andy, you
I'm
want
not
to
sure
take
I
that?
understand the question.
So that would be where you'd use like a P1M pump, a variable volume piston pump with a PMAC motor versus a straight fixed displacement pump, right? Because we do have applications that benefit from using the combination of the two.
Yeah, so I think the variable displacement pump where it shines is when you're trying to hold a load for a long period of time. You can really reduce the displacement of the pump while you're maintaining pressure, and then you have less torque required from the motor. So think of like a lifting arrangement where you're lifting a load and you want to hold it as you're driving to a spot. Holding that load in place with a fixed displacement pump consumes a lot of power and requires a lot of torque out of the electric motor. Whereas if you use a variable displacement pump, you can reduce the displacement of the pump, maintain the pressure, and hold the load.
Great, thank you. Do you have ready for use ePTO unit / set for 650 volt motor plus pump plus control?
Yeah, so we have some packages that we've designed specific for OEMs where we have what we consider an ePTO is the ePump plus the inverter plus maybe a cooling solution and all the cabling and the cooling lines, and we can put it in, you know, a nice box that can be mounted on a vehicle. So we have some solutions we've made for specific OEMs, and we have a brochure that's available online that kind of shows that. But we don't have any, you know, off the shelf, I guess, items because it's very OEM specific on how they want to mount that and package the components.
Great. Thank you. What are the common voltages for ePump applications?
So I'll take a stab at that. So obviously it depends on the vehicle architecture. And so you do have some sectors that still are operating low voltage, 24, 48, mainly 48, right? Up to 96 volts. You know, most of your on-highway ePTO is nominal 650, right? Max 800. There's talk about going higher, you know, 850, 950. There's a lot of chatter, but most of your off-highway stuff is between 300 and 650. And, you know, you do get even hybridization where you're using a diesel engine and maybe a small battery pack for the hydraulic function that could be DC. So there is no one voltage, but generally, you know, 650 is kind of the center of the dartboard, right? But we have customers that are all over. And obviously you look at the min and the max, but we do have a lot of DC applications. We have a lot of low voltage DC applications still too, but I think a lot of those customers are considering going to high voltage just because there's a lot of practical advantages.
Great, thank you. What does your selection tool include? Oh, sorry, start that again. Does your selection tool include northern climates where ambient temperatures can be as low as minus 40 degrees C?
Yeah, so I'll take that since I've worked on the selection tool. And so you've got a couple considerations with cold weather and high elevation. So number one, selection tool is what I would call a beginner tool, to be very transparent, right? It is to get you in the ballpark, get you some basic information. And then if you're not experienced, talk to an apps engineer, whether it's a Parker person or one of our channel partners. Whenever we get into extreme environments, right? High northern, high heat, high altitude, that takes a little different consideration. The sizing tool does not have today's version, right? And this is software, so it's always evolving. I can tell you there's probably 5 more enhancements planned for our next fiscal year. We do not have thermal modeling in that tool. We do have it like at a PhD level. I mean, and not to be, you know, flippant about it, but that's we do have tools in both Europe and the US that were designed by you know, electrical engineers, doctorates, electrical engineers that can account for all those things. So what I would tell people is if you are in a more extreme application, or you want to understand field weakening or thermal effects, give us a call. We can run a simulation model. Our app engineers have access to that tool. It's very powerful, in both Europe, US, and Asia. So yeah, there are limits to what the sizing tool can do. I wish it could do everything today, but hopefully there'll be some version in the next year or two that can do what the upper level tools can do.
All right. Thank you. We've still got 5 minutes left, so we'll crack on with still a few questions to get through here. What options are available for the 3-phase motor connections on the PMAC motors? IP67 rating? Question mark. I have experienced failures in terminal lugs on other mobile motors.
So we have, and I'll let Andy supplement, but we've recently switched with design changes started about 1.5 years ago to standardize on the power lock connectors. So the Amphenol power lock, they're very popular in electrified systems. They do provide that level of protection you're looking for, both from water ingression. They also provide what's called an HVIL, which is a vehicle interlock. In case of a short, it communicates back to the inverter. So they're a positive locking connector. Depending on the current rating, we have a 300 series and a 500 series. But power locks are our primary today. They're the default, but we do offer other options. And I don't know, Andy, if you have any observations from your end.
No, I mean, just to add on that, obviously we know these, off-road mobile equipment is in very harsh and extreme conditions, right? Dirt, dust, mud, the environment, as well as heavy vibration and shock loading. So our motors and our ePumps have been shock and vibe tested, to the standards. And in addition to the power lock, we have terminal box options and some other things that might be appropriate depending on where the ePump is in your machine.
Excellent. Thank you. Have you found the need to use a refrigerant to keep e-motors cool for a construction application?
I don't think so. I mean, usually the water ethylene glycol from the machine radiator is sufficient at 60 degrees C is kind of the standard that we calculate based upon. So usually that's sufficient. I guess as Rich mentioned, there's always extreme conditions, right? If you're working on the equator, especially this year when it's 120 degrees in some regions of the country, maybe that could be a benefit, but I haven't seen that personally.
Right. Thank you. I think so. A few questions coming about the spline, the tolerance class used for the spline connection, the typical surface treatments and hardness for the pump and motor splines. Can you talk about that a little bit just before we finish?
Yeah, I can try to address that. So, I mean, we tend to keep our tolerancing and our heat treatment methods, somewhat proprietary, and certainly on an open forum like this, it's not appropriate maybe to give those out. But if you want to work with Parker, we certainly would share those kind of details as we get deeper into the discussions on your needs, right? And the nice thing with an ePump is if you buy the complete ePump from us, you don't have to worry about any of that because we're taking all of that internally, and we're taking responsibility for all that, right?
You'll take care of it, so it's done and dusted.
Right. Yeah.
Great news. Okay, well, look, I think we're sort of that's probably a good place to wrap up. We are just nearly at the hour, so there are a few more questions. Apologies if I didn't quite get to every question there, but I know our experts here will be able to reach out and contact you afterwards. As I say, contact them if you would like to get the slides. I'm sure this conversation will keep going with all the people registered here, all the people viewing, and people watching on demand afterwards. So thank you very much, both of you, for a really interesting hour. And we'll keep the conversation going in the magazine, and see you in Chicago.
Yep.
Yeah. Thank you, Tom. Thanks for hosting.
Yeah. Appreciate it.